refactor to use a decorator. And the reason why I wanted to start with save method is because it's the simplest of the two, because it's a command. We can also apply a decorator to the read method. But before we do that, we need to look for behavior that the implementation of the read method has in common through all of those lines of code. Just before, we can start to look at those lines of code and try to figure out what do they have in common. Do they have anything in common? So list of log with reading is an ID. And then we have list of cache with get or add, which also takes an ID or delegate. And then we have list of log with return, which is an ID, list of log with find, which is an ID. So it seems like all the methods here take an ID as input. Some of them are commands and some are queries. But the really problematic part here is the cache.get or add, because not only does it take an ID, but it also takes this factory delegate that we need to supply to it. So let's have a look at the get or add method as it's defined. So it takes the ID and it also takes this list factory delegate. And the reason why it does that is because it should use that list factory delegate to add to the cache if the element is not already a member. But since the get or add method already returns a regular string, we actually have a way of knowing whether or not the element is in the cache. Not as an atomic operation, but just as a normal operation. We can say, we could ask the cache if it contains that ID, because we can look at the AD and see if the AD is empty, the cache does not contain a message for that ID. And if the AD is populated, it means that the cache actually contains an element for that particular ID. So what happens if we remove the message factory delegate? Now obviously the name get or add is totally wrong. It should just be get or read. I'll change this in a moment, but let's just go back to the consuming code and see what sort of consequence that change had. If you look at the read over there, it first calls list.log with reading as it did before, and then it calls list.cache to get or add. So it calls into the cache much earlier than before because it needs to figure out where the message is actually already in cache. So again, get or add is not a good name, it should just be get or read, but for now, we'll just do only that at a time. But the returned message is a linear string. So what we do now, we can try to examine whether we found the message in the cache or not. So if not message not any, that's a very roundabout way of saying if the message is empty, then we'll try to use store and try to read the message itself. So we'll say list.store of the all text of the ID, and that returns a linear string as well. And we'll just assign that linear string to the same message variable. And in this case, if the message does contain a value, so if message any is true, then we can add that message to the cache by using this cache and save. And in this case, then safely call message with single because we check whether the message any is true. And now, if the original message we got from the cache didn't contain a value, we just skip this entire block. So now we can look at the message as it is, either from the cache or from the store. And then we can look at if the message contains a string, then we'll log that we are returning the message, and otherwise we'll log that we did not find the message. So that's just the way that we can reflow this particular logic without changing the basic ways of the system. So now we have methods where all methods just take an ID. And the only exception to that is the call to this cache.save, which also takes a message as input, but that's not problematic because the message is just returning a variable here in the input message. So it's not something that has to be passed to the outside. So now we have lots of methods that just take an ID as input and return a little string. But they have so again, names are not particularly interesting. So first of all, I promised that I would change the name of get or add into on top of that read, for example. You can also change the name of my store, read all text. There's no reason that it should be called read all text. That's just a residual from all the read methods that we did earlier on. So we'll just rename this to read as well. And if we do that, we now see that we have log the reading, cache the read, store the read, log the return, log the read.find. So we're not quite there yet, but we're kind of approaching to those that we want to do. So So if we look at the original iStore interface, which is one of those extracted header interfaces that we invite, we could take the read method here and say, what if we just define a role interface for iStore reader that has that read method defined as the same method. And if we do that, we can start to apply the decorator pattern. So store cache example here already implements the iStore writer interface, but we can also have it implement the iStore reader interface because it already has the read method down there at the bottom. So this is the pass because the read method has the same signature as the iStore reader defines. But now we can make store cache a decorator not only of iStore writer but also of iStore reader. And the way is then first to take iStore reader as an input into the constructor and assign that input to a class reader. So now we have a reader as a writer. And then if you look at the read method down there in the bottom, what it does at the moment is that it tries to get the value out of the cache, and if there is a value in the cache, it returns the value, and otherwise it just returns name. But now that we have an inner reader, we can do something more interesting. Because what we can do is still, if we find the value in the cache, we'll just return value. But if we don't find the value in the cache, we can try to read through the underlying reader by saying, is the reader a read? And then we can do the data return that we can see. If that has a value, we can add it to the cache. And then no matter whether or not where the cache contains something, we'll return that as the return value for the read. So if you're familiar with cache patterns, this is called the read cache. It's also, as we talked about before, an around device. So everything seems to fit very nicely. And we're not really inventing new stuff. We're just rediscovering things that other people have already discovered before us. It's always a good thing to do that means we're following the right track. Again, I'll remind you that if you squint a little, that call to this the reader of read, you can almost imagine that that's a call to base of read. But the difference here is that now we're composing both a reader and a writer. So the decorator used in this way is a way where you can actually simulate multiple inheritance, but it's just multiple positions of multiple inheritance. So this is why decorators position in general is much more flexible than inheritance. So now we have this decorator of the reader. We can simplify the reader because now we just say this is the cache of read. And then we just look at the message to see whether or not they are returned. So imagine we have hundreds of calls spread throughout the code base that first tries to get something out of the cache, and then if it doesn't find it with the cache, then it calls into some underlying storage mechanism and tries to pull the value out of that underlying storage mechanism. And then if it gets the value, it writes to the cache, and then it returns the value. So if you have that spread out throughout hundreds of different places in the code, this is very much more valuable because now you have a single place where you have this behavior. So if you ever need to change the read-through cache behavior, you can do that place. And it also becomes much more easier to understand what is actually going on in this particular code because that's just an implementation so that there is a cache involved. It doesn't mean that any of the other aspects will be more. So if we want to look at the position, you can see that the cache is now a store cache of file store and file store. But that's a very common pattern. The reason is that file store implements both iStore reader and iStore writer, but store cache doesn't know that. It just knows that it depends on the reader and writer. What happens here is that file store, because it implements two different interfaces, plays two different roles, but it's still the same interface. And that's a very normal thing. You not always bring these decorators at this place, but it's not particularly surprising when it does. It happens from time to time. So this is also an example of the file store class, which has nice appearance, but it plays with roles, so it's still very decoupled. You have other clients of the file store class which do not talk to file store itself, but talk to the interface, and those clients are decoupled from the file store itself, even though file store has nice appearance. Because that's otherwise often a problem that if you have more neatly coupled code, computers tend to suffer. This is one of the ways that you keep coherence and still have neatly code. Now let's also make store locker a decorator of iStore reader. So first, in order to make an iStore reader, we have to take in an iStore reader itself, because iStore reader is a query, and we can't provide a degenerate implementation of the query because we have nothing to return. So we take in a reader and assign it to the top field, and then that enables us to implement the read method, not by adding an date method, but just by calling into this reader method and return that. But now that we have all this stuff set up, we can add another dark device around the course of this read. We can say, or we'll log that we're reading the message, and then after we've read the message, we'll log either that we have returned the message or that we will find it. So that's another around device. And then we can go back and look at the position here, and now you can see that if you look at the bottom of the screen, the read method has elapsed into just call to this reader of read as the same method early on without a single call to this method. So we haven't seen this read property yet, but that's just another one of those two properties that I don't like, and we'll do those eventually. And you can also tell the constructor that the last line of the constructor is this reader is assigned with a L, and that is this reader. Lowercase r in the reader itself is this reader with the properties of the state patterns. So if you look at the constructor here, the variable L is an instance of store locker, and you can tell that store locker takes C and C. And again, C in itself is store cache that takes file store. So you see this recurring pattern here around that file store plays two different roles. It plays the role of the writer, but also the store cache itself plays the role of the writer, and so on. So that's not at all surprising. This is something that often happens, not always, but in this case does, and gives us a fact that this is actually how you simulate those comparisons. What you just saw was a consistent application of the decorator pattern. But there's still a bit of residual noise left over in the code, so it's time for a final cleanup. So right now, if you look at the message store, it looks like this. So this is the top of the message store. It has 6 class fields and quite a busy constructor. And 3 of the fields, iStore cache, iStore locker, and iStore, are header interfaces that are extracted along the way, but which are no longer in use. And the iFile locator and the iStore locker and the iStore reader interfaces are those role interfaces that occurred because I refactored to use decorator principle. So we'd like to get rid of the header interfaces, and we'd also like the constructor of the message store class to be less busy as it is. And also it would be nice to get rid of all those factory properties. So there's 6 of those factory properties at the moment. They are still relying on inheritance. We'd like to favor composition over inheritance. So there's just one last step in order to get rid of all of those factories. So if you imagine that I've raised a batches 1 over this, I could batches something like this. So notice that I've removed all the header interfaces. Not only have I removed the header interface fields, but I've actually also deleted those 3 header interfaces from the entire code base. So that leaves this store with only 3 role interfaces: iFile locator, iStore writer, and iStore reader. And those are the dependencies of the message store. You will also notice that the message store constructor have changed, because if you really want to apply the dependency inversion principle, you shouldn't really care about exactly how those interfaces are composed. A third party can do that to meet the needs that that third party actually has. And the message store should really have no opinion on how those things are composed. So instead of trying to compose those 3 dependencies within the message store constructor, now the constructor just says any third party that needs to use message store should supply those 3 dependencies to the constructor. You'll notice that it protects its invariance because it has dark boxes around each of those 3 dependencies, and it just assigns the dependencies to the fields. And the implementation of message store just now looks like this. So the save method just calls the save method on the writer, the read method just calls the read method on the reader, the file info method just calls the get file info method on the file locator. So in this case, you would probably argue that the message store class that you're looking at here is entirely redundant. And that would probably be true. Now all the aspects that you refactored away, like caching, logging, and persistence, those are what we typically tend to call cross-concerned. And in this case, that was actually all there was. There was no business logic involved in this class to begin with. But if there had been business logic, that's actually what we would have been left with in this message store class. So if you have some business logic, that's where this ends up. And all the other stuff that has to happen, like caching and logging, can be factored away as decorators. So if you have business logic, this is what business logic will actually do. And then you have this orchestrated class, and that would actually do add value. So depending on whether you have business logic or not, you may want to remove a class like this, or might want to keep it. Now, as I promised you, we no longer have to rely on inheritance for any of the extensibility. So the message store class and all the other classes are still adherent to the open source principle, but it's no longer necessary to rely on inheritance in order to make this work, because store cache now implements ISO writer and ISO reader, those two role interfaces. So it's entirely possible to remove the virtual keyword from the store cache class. So as I told you before, it's not that it's problematic that those implements are virtual by themselves. I'm just moving the virtual keyword here in order to demonstrate that it's possible and we are not at all relying on inheritance. And I can do the same with the file store. I can just remove the virtual keyword from those three methods, because each of those methods now participate in those three role interfaces that the file store implements. And finally, we can look at the store locker. So the store locker now implements ISO writer and ISO reader. That actually didn't bring about out to the store locker class. So the save and reader that actually never got the virtual keyword. But there's another thing I want to do with the store locker, because at the moment, the save and read method, the way that they actually implement logging is by calling locker information and locker debug. And those are static methods on a static class. And you could argue that if we really want to follow through on the dependency inversion principle, we should also invert the dependency on this locker information locker debug API. So instead of using those static methods, what we could do instead is we could inject an iLogger interface and then assign that locker to the class field and then change in the save and in the read method the calls to locker information to calls to this locker information and this locker debug. And if we do this, a third party could compose a message store like this. So this is just one example of composing a message store, but this is the example that corresponds to the behavior that we have all along since we started out with the implementation before we even started refactoring. So sometimes when you read composition code, it's easiest if you read the composition code from bottom up, if you will. So if you imagine that you have a client that needs a message store, you create a new message store. The message store needs a writer and a reader and define a locator. So in this case, we just pass log, block, and file store. And then if you want to know what log is, it's in store locker. And store locker needs the iLogger interface and needs a writer and a reader. So we pass in log, and cache. Because the cache is a store cache and it implements both the reader and the writer interfaces. And again, the store cache requires a writer and reader, so we pass in file store twice. And file store is an instance. A file store is proper directly in the instance, and locker is an implementation of the iLogger interface created through this new locker configuration of the locker. So this is just the composition configuration, if you will, that corresponds to the initial code base that we start out with before I start refactoring. But if you want to change how the message store is being composed, you can just change this composition code. So if you don't like the store cache as it is at the moment, this is just using a dictionary. And if you want to replace that with a proper cache implementation that has expiry and eviction strategies and so on, you can just create a new class that implements the appropriate interfaces, the writer and the reader interface, and you can do that by adapting whichever caching library you want to leverage. And then instead of using this particular store cache concrete class, you just use your new adapter class that adapts to your caching library of choice, and then you can compose that into the message store utility. You say store logger, you can replace file store with SQL store and so on. And you don't have to change any of the message store code or any of the other implementations of the interfaces. You just need to replace whichever you want to change. So the final class diagram looks like this. So you have message store, which consumes those three lower interfaces. And you have store logger, store cache, and file store, that each of them implements some of the interfaces. Some of them implement all three of the interfaces, and some of them implement two of those interfaces. And what you can see here is that all the details depend on the abstractions, but none of the abstractions depend on the details. So this is the implementation principle applied to this particular code list. To summarize, SOLID is a set of 5 principles. The single responsibility principle, which tells us that a class should only have a single responsibility, which means it should only have a single reason to change. The open code principle, which tells us that a class should be open for extensibility, but closed for modification. The list of substitution principle, which tells us how polymorphism should work, that it should be possible to change the implementation of an interface without changing the readiness of the system. The interface segregation principle, which says that clients should own the interface that they consume, and they should only depend on the methods that they use. And finally, the dependency principle, which states that abstractions should not depend on detail, but details should depend on abstractions. Keep in mind that SOLID is not a goal in itself. Part of the reason for that is that there's no way to measure whether we actually reach that goal or not, so it's not a good goal just in that case, but also because SOLID is a reaction to certain design spells. So if you have a design spell like viscosity or rigidity, SOLID is probably going to be a strategy in order to potentially address those problems. But you have other design spells that are not related to those design spells, and if you have other problems with the code, then SOLID may not be the answer. So keep that in mind. SOLID is a good answer to certain types of problems, and if you have other problems, there's probably also likely to be other solutions to those other problems. The mental image you need to have with SOLID is not something that is rigid or brittle, but rather something that's supple, pliable, which will enable you to change direction or otherwise deal with changes in requirements and actually move it on. So those are the SOLID principles. They are also known as the principles of object-oriented design. So if you really want to create object-oriented designs, you should know and understand these five principles and apply them whenever it makes sense. That was the same method refactor to decorator. And the reason why I wanted to start with the same method is because it's the simplest thing to do, because it's command. But we can also apply a decorator to the read method. But before we do that, we need to look for the behavior that we Hello, my name is Mark Seaman, and this is the 8th and final module of the Encapsulation and SOLID course. This module is about the coffee maker code example. So what exactly is the coffee maker code example? Well, the coffee maker code example is a published problem description about this Mark IV special coffee maker. And the problem description was created by Robert C. Martin, and I think he originally described the problem in his book, Agile Principles, Patterns and Practices in C#. This is a book I highly recommend if you're interested in learning more about SOLID, because Robert C. Martin is the author who originally assembled and described the 5 SOLID principles, and this is the book where he describes the SOLID principles in terms of C#. There's also an older version of this book that describes the same principles in terms of Java code, but in this case you can learn about them in C#. So I highly recommend that you read this book, and you can also read about the Mark IV special coffee maker there. But if you don't want to do that and you just want to see what's the Mark IV special coffee maker all about, the problem statement in itself is also available directly on the internet. And it's called Heuristics and Coffee, that not only describes the problem but also provides Robert C. Martin's sample implementation of that particular problem. So that's actually pretty interesting. And if you really want to have an exercise of this, then go and download that PDF file and do the exercise and see where you end up with before you actually continue looking at this module. And then afterwards you can come back and compare your implementation with the implementation that I created. Here's the Mark IV special coffee maker problem statement as Robert C. Martin described it. The Mark IV Special makes up to 12 cups of coffee at a time. The user places a filter in the filter holder, fills the filter with coffee grounds, and slides the filter holder into its receptacle. The user then pours up to 12 cups of water into the water strainer and presses the brew button. The water is heated until boiling. The pressure of the evolving steam forces the water to be sprayed over the coffee grounds, and coffee drips through the filter into the pot. The pot is kept warm for extended periods by a warmer plate, which only turns on if there is coffee in the pot. If the pot is removed from the warmer plate while water is being sprayed over the grounds, the flow of water is stopped so that brewed coffee does not spill on the warmer plate. The following hardware needs to be monitored or controlled. The heating element for the boiler, and it could be turned on or off. The heating element for the warmer plate, it could be turned on or off. The sensor for the warmer plate, it has 3 states: warmer empty, hot empty, or hot not empty. A sensor for the boiler, which determines whether there is water present. It has 2 states: boiler empty, and boiler not empty. The brew button. This is a momentary button that starts the brewing cycle. It has an indicator that lights up when the brewing cycle is over and the coffee is ready. A pressure release valve that opens to reduce the pressure in the boiler. The drop in pressure stops the flow of water to the filter. It can be opened or closed. The hardware for Mark V has been designed and is currently under development. The hardware engineers have even provided a low-level API for us to use, so we don't have to write any bit-driven I/O driver code. The code for these interface functions I'm going to show you in just a moment when I'm switching to the code. But if the code looks strange to you, then just keep in mind that it was written by hardware engineers. I'll now switch to Visual Studio and show you my implementation of this problem. So it's not the implementation that Robert C. Martin gives in his observation in the book, but it's my implementation. And you can really take those 2 implementations and compare them to each other if you think that's interesting. So this also outlines that there is not a single way of writing solid code. This also reinforces my point that you can't measure solid because there are various different ways to write solid code. So take a look and compare it to your own solution or compare it to Dr. Martin's solutions, and there are also other solutions that are on the internet. The first code I need to show you is that was given to us by the hardware people, and that's the interface called a coffee maker here. And as Robert C. Martin stated, this may look a little strange, but that's just because it was given by hardware people. So that's not something we need to implement, but that's an interface that we need to tune in order to create all the controllers that control the coffee machine. So the first function that we're looking at here, get warmer plate status, as it says, this function returns the status of the warmer plate sensor. This sensor detects the presence of the pot and whether it has coffee in it. It returns a warmer plate status, and all of those status types are defined at the bottom of this file with just columns. The next method is this get boiler status. So this function returns the status of boiler switch. The boiler switch is a float switch that detects if there is more than half a cup of water in the boiler. And it returns another status, the switch is another end. And the third method here, get brew pot status. This function returns the status of the brew bottom. The brew bottom is a momentary switch that remembers its state. Each call to this function returns the remembered state and then resets the state to brew pot state of the switch. Thus, even if this function is cold and there is no rain, it will still detect whether the brew pot is pushed. So I had a little bit of problem understanding what this does, and my interpretation when I started to think about it compared to the more verbal description that Dr. Martin supplies is that you press the button and the next time you call this get blue button status, it actually tells you that the button was pressed, and then it resets to blue button not pushed. But the thing that I found difficult to understand about this whole description was that the blue button is also an indicator, so it also indicates that the coffee machine is actually ready. So you can imagine that's a button with a light in it or something like that. But the point here really is to understand that even though the blue button is only a button, it actually has two functions, because it's both the thing that can trigger an action when you press it, but it's also an indicator that can show whether the coffee machine is ready, and those are two rather decoupled things. So you need to understand that even though it's a button in both cases, it actually serves two purposes. Anyway, these three methods are all get methods. If you notice, there are more methods further down, I'm going to show you those in a moment, but these three methods are the get method. Those are the queries. All three of these methods return a value, and we don't really know how it's implemented, but I think it's safe to assume that there will be no side effects that need that all those methods. And actually, there is a side effect in get blue button status, because if the blue button was pushed, then calling that get blue button status method would actually reset the state of the button to blue button not pushed. But so that's just something that we need to keep in mind here. So further on down, there are four set methods. So there's this set boilerplate state method. This function turns the heating element in the boiler on or off. And there's also a set warmer state, which turns the heating element in the warmer state on and off. And then we have the third set method, set indicator state, and that's the indicator light on the button. So this function turns the indicator light on and off. The indicator light should be turned on at the end of the blue cycle, and it should be turned off when you click this at the blue button. So that's what I really had a little bit of trouble understanding until I started to think about it. And the fourth set method here is set the leak valve state. This function opens and closes the pressure leak valve. When this valve is closed, steam pressure in the boiler will force hot water to spray out of the coffee filter. So that's basically what it means to do the coffee. When the valve is open, the steam in the boiler escapes into the environment, and the water in the boiler will not spray out over the filter. So in this case. So these four methods are not queries, they are commands. So we would expect those to change the state of the hardware when we call them. And then we have all the various return types and true values. And those are, as you know, all denote values, various denote values, mostly on and off, also true, and the warmer state status, which is a tri-state in warmer energy, hot energy, hot not. Which the first case is when the warmer itself is empty, that means there's no pot on warmer at all. And then the next state here is when the pot is on the warmer, but somehow it can detect that it's empty. And the third state here is when the pot is on warmer and it's not. Some amount of so that's basically the interface, the hardware interface that we were given. And our task then is to figure out how to create some sort of controlling software that will control the entire coffee maker based on the API that we given here, based on the requirements that are put into the environment software. So I looked at this a little bit, and I thought that it looks like those three methods that we're looking at the moment, the queries, we'll need to code those at some interval in order to figure out what's the state of those different sensors. Then, based on the input from those sensors, invoke one or several of these commands here to change the state of the hardware. So I was thinking a little bit about how to do that, and then I thought that, well, this is probably a pretty good fit for the observer pattern, because we have hardware that produces data, so every time we code those three queries, we'll get some data back, and we'll need to act on that data. And sometimes we need to act on a combination of things that arrive from those different sensors in order to figure out what's going on. And then based on the observations that we get from those sensors, we need to react in order to actually control the hardware. So it sounds to me like the observer pattern is a great fit for this particular problem, because the observer pattern becomes described when you have one publisher that publishes event, and you have a set of subscribers that are interested in knowing about these events. That's basically what an observer is. And in this case, we just have several publishers instead of subscribers. It sounds like the subscriber should split the observer. So let's try that and see where that is us. The simplest rule of the requirements concern the warmer phase. So let's start by looking at the warmer phase first. So what I've done here is I've simply created a class called warmer plate, and then I've decided to implement the iObserver.t interface. So instead of defining my own observer interface, I would have had to do that 2 years ago, but now iObserver.t is actually part of the framework itself. So you see here it's implemented in its folder, and it's part of the existing namespace, so it's a very fundamental type in .NET, even though it doesn't really have any input. That's what I understand. And as you can tell, iObserver.t defines the methods. So onCompleted is if you have an observable stream of events, and that observable stream will stop at some time, so the stream will actually stop at producing any more events. The stream will call uncompleted, and that's not really the case in this case, because we will start calling the hardware to figure out whether there are any changes in the state of the hardware, and we don't really expect to ever stop calling. Maybe we will have some sort of shutdown routine which actually wants to turn off the calculator, but that's not the case. So undo with it. OnError is another method that's supposed to be called in the producer of the event stream, the publisher of the event stream. Ever experiences some sort of error, and it needs to inform all of the subscribers that it experienced an error, and when that happens, it can actually call this an error on all of its subscribers. And that might be something that could happen, but we'll just ignore that. So the only one that we're really interested in is on next, and on next just provides the next value of t, so that's just the next given value that we'll get from content. So that's actually one that's really interesting. So warmer plate, I'll make that an observer in this case of warmer plate status. So the part of the hardware that publishes this warmer plate status, but that simply means either warmer empty, hot empty, or not empty, so just take the back before, will monitor, or the warmer plate will monitor this precipitation stream. And when it monitors this precipitation, it also needs to be able to send commands to the hardware or to change the state of hardware. So not only will it observe a stream of warmer plate status values, but it also needs to reactivate values, and in order to do that, it will need an instance of the iCoffeeMaker interface itself. So that's the hardware interface. So the way I do that is simply by using the integration principle, and say, in this case, I use constructor injection, and just say warmer plate has a requirement that it cannot work without an iCoffeeMaker instance. So this is also encapsulation in the sense that now warmer plate is statically advertising that it's part of its invariance that it needs an iCoffeeMaker. And because we have this coupler, we can't declare statically that the iCoffeeMaker instance cannot be null, or we add this null after in order to fail fast. If someone buys this fast null, this is but otherwise, I'm just going to save the hardware interface later. And then we implement the iObserver interface. And the only thing that's interesting here is just to implement the onNext method here. So every time a new warmer plate status value is produced, this onNext method is going to be called. What simply happens here is that we look at the value there and say, if the value is hot, not empty, we'll just set the warmer state here to what is on. And I expect this to be an inclusion operation, so even if it's already on, it doesn't really matter that I call it performance on in. And if the value is not empty, then I'll just simply ask the hardware to set the warm state to warm state off. And that's it. This follows the same stability principle because it really only has one thing to change, that is the rule about how should it react to warmer plate status values. If that rule changes, then we need to change this class. It also follows the open source principle in the sense that if we want to change the implementation of iCoffeeMaker, we can do that just by providing another implementation of iCoffeeMaker. It's an open question whether this particular class actually adheres to the viscous substitution principle because it depends on how I populate, and this was an interface that was handed down to us from the hardware engineers, and that interface actually has not just one single method, it actually has several methods on it. So not a roll interface like the roll interfaces that I typically might have with an interface with a single method. So we also see that this warmer plate class may violate this specification principle, or rather the I-copulator interface violates the specification principle because the warmer plate class here depends on methods on I-copulator that it doesn't use. It turns out not to be a problem in this case, but otherwise you could resort to a technique that evidence used to make a design called an anti-corruption layer. So I could have defined my own role interfaces that adapts over the I-copulator interface. So it turns out, in reality, it's not really a problem here. So I just left it as it was in order to this sample. And then the warmer plate also follows the principle because you're just getting I-copulator from the outside. So any third party that was connect warmer plate together with other classes or other objects can just find whatever it is to find. So it doesn't really depend on specific details. It just depends on the I-copulator abstraction. You know, the party that abstraction is perhaps not the abstraction because it's not really abstraction. So it doesn't really depend on details. So that's fine. So let's look at another part. The relief valve is just about as simple as the warmer plate. So I'm not going to walk you through that in the same way of details, but it's actually also an eye observer of warmer plate status. So it looks very much like a warmer plate, but I still think it makes sense to have two different classes, even though they constructed generic interface here. So eye observer of warmer plate status in both cases. But the action that it performs when it gets a warmer plate status value is a little bit different because what it does here is instead of controlling the warmer plate itself, it controls the relief valve. So in this case, it says if the value that's applied to it, this one, if that value equals warmer plate status or empty, then it sets the relief valve state to relief valve state to open, and otherwise it sets it to close. But apart from that, it's just about the implementation as you saw with the other case. Another piece of hardware that we use to control is the boiler, and that's a little bit more complicated. Let's look at that. So here's the boiler class, and it doesn't just implement I-observer of a single event stream, but it actually subscribes to two different event streams. So it's an I-observer of blue button status, which indicates whether the blue button was pushed or not pushed. And it's also an observer of this boiler status, which indicates whether the boiler is empty or not empty. So given the combination of those two events, or those two hardware states, if you will, determines how the boiler is actually being controlled. So just like before, the boiler class depends on the hardware interface here, I-copulator. So again, there's a bit of encapsulation or particular variance going on here because it uses the constructor to advertise that it needs an I-copulator, and then if someone tries to cheat it, then I'll say no, it will exception. In this case, it also needs to be state, so it needs to figure out whether the boiler actually has water or not. So there's no particular sensor in itself that tells us whether the boiler has water. So this boiler class here could ask the hardware whether or not the boiler has water or not. When I created this implementation, I thought it would make more sense to simply just subscribe to the stream of data that arrives about what's actually in the hardware build, and then just react to whatever happens. Just react to the population that remains as they go. So this may not be the simplest possible solution, but it was just what made sense to me at the time when I created it. So again, there's many different ways you can run software. There's not a single event that do that. So basically what we do here, we have two on next implementations because we are implementing our observer of both blue button states and of boiler states. So we are observing both those to identify whether the blue button is pressed and whether the boiler has water. So in this case, we need to keep track on whether the boiler has water. So this is a Boolean value, and the default is false. So what we do here when we get a blue button status value is to say, we will only change state of the copulator if it actually has water, and by default that is false. So this particular if statement is not going to evaluate true unless the has water flag has changed. And there's no way that it's going to change in this particular implementation on next. So we'll start by going down here to the other implementation on next and have a look at what happens here. So basically it says if the boiler states value that arrives, if that value is not empty, then we know at that point that the boiler had water. So we set the has water flag to that particular state. And then if it doesn't have water, we set the boiler state off. So if we detect that the boiler is now empty, we also have to stop the water heater in the boiler from heating. But this is how we set the has water flag. And then if we look at the implementation up here, if the boiler has water and also the value is blue button status pushed, then we set the boiler state to boiler state on, which means we turn on the heating element in the boiler. The last piece of hardware we need to be able to control is this indicator line. That's the most complicated, so that's why I say it for last, but it's not that much more complicated for the control. So again, the indicator class here is an observer. It's actually an observer again of two different event streams. So again, it's an observer of boiler status, and then it's an observer of blue button status. And we do pretty much the same things with direct encapsulation and particular variance. We read the iCoffee data instance and we advertise that to the constructor and make sure that the iCoffee data instance is not null. And then, just like before, we have this flag that indicates whether or not we think that the boiler actually has water in it, but we also have another flag that indicates whether we are currently moving. So again, one alternative implementation might be to simply ask the hardware. We have the hardware field here already. You might actually ask the hardware whether or not it has water, but you can't really determine whether it's brewing or not, because even if we ask the blue button, but the blue button stays is, it might be off because it switches off after the point. So we need to keep track on whether or not the coffee is actually brewing now. So in order to do that, that then happens through an exchange of those two on next implementations. So again here, we detect whether or not we have water by evaluating if the value that is passed in its boiler state is not empty. It means that the boiler has water. So we simply set this flag by the boiler status. And then if the coffee machine is currently brewing, and it's not by default because this is another boolean and the default is false, let's get back to this in a moment. But if the coffee machine is currently brewing and the value here is boiler status is empty, it means that at that case I need to stop brewing, which means that I need to ask the hardware to set the indicator state to on and set the brewing to this false. So again, this is one of the things where I have to read the requirements document a couple of times, but basically the indicator should turn on when the brewing cycle is done, and that's actually what's happening here. So the indicator is on means that the brewing cycle is finished, which means that it's ready, so that's basically what's going on here. And that also means that this brewing is set to false, that's the case. And the other status update we get from the hardware here is the blue button status. So again, we test whether or not we have water. So if we have water and the blue button status, this blue button is pushed, then we start the brewing cycle, and that means that we set the indicator state off, which means it's no longer ready, the coffee is not ready at the moment, and we also set this brewing flag to true. And just as before, on completed and on error, are the same things. One of the nice things about this design is that it's very easy to unit test. So I actually have unit tests here. So if I run all my unit tests, it just says, probably you can see that down in the corner here, it says 41 passed, 0 failed, and 0 skipped. So all the tests are actually passing. Let's just look very briefly at one of the tests. So let's just do the test of the normal date, that's the simple one. So basically, I just have a set of tests here. You can see there's a one-liner and one-liner, and another couple of lines of code here. The one-liner test. The test that takes 3 lines of code to set up and evaluate. And one takes 3 lines of code, and one takes 3 statements. So that's pretty much it. Very, very easy to use this sort of design. And that's also always a good indicator of whether or not you have a solid design. It's not guaranteed that it can easily resist a particular proteins that it has a solid design, but in my experience with this interaction, if you do unit testing, in particular if you do test-driven development, solid design is something that works very well with the unit testing. So the solid design is always easy to do test. So finally, we have all the building blocks in place, and now we just have to compose all of those building blocks together into a program. So I have a little console program here because I don't really have a real hardware copy maker of this particular design, but so what I've done here instead is I just created a little console application that has a fake coffee maker in memory. So coffee maker in memory here is my implementation of the iCoffee maker interface here. This is not particular issue, but it just simulates the hardware without having any hardware. So it's just an indicator. So what you can do here is that I'll just start by setting some default values to hardware because I think that the read validation should be closed at the beginning and the pod should also be closed. And I've talked a little bit about the funny thing about the iObserver of T interface that's defined in the system namespace, is that it doesn't really have any implementations in the .NET-based library itself. It does have implementations in this extensibility package that's called reactive extensions for .NET. So reactive extensions for .NET is this open source package that Microsoft still produces and that you download the NuGet and install in your system. And those NuGet packages contain various implementations of iObserver of T and iObservable of T, and lots of interesting things to do that. One of the things that you do with reactive extensions is that you can set up polling consumers of all of the event streams that you included. So in this case, the hardware API that I have at the moment doesn't really provide an event stream by itself. It just provides methods that I can call. So one way that I can call those methods is by setting up an event stream by using reactive extensions. So what I can say here is I can say observable physical time span from seconds 1. So this pretty much just means that there will be an observable event produced by this factory method every 1 second. And this particular event that's being produced is just an event without any data in it. So what I need to do is I need to map that data into a call into the hardware. So in this case, I map that trigger, if you will, into a call to the hardware that get blue button states. And that get blue button states, if you will, a call returns a blue button status values. So now I have that every second one of those blue button status values are